We are now going to start solving the exercises of abstract algebra by Gregory T. Lee. I asked whether you need something specific since I did not get any answer to that. So I'm going to attempt all the exercises. Okay, starting from the very first one. So here we are given two sets S and T, and for them we need to calculate these sets. So S intersection T first. The only common element is 3. So we have this. Then S union T. 1, 2, 3, 4. S difference T is the set of those elements in S that are not in T. That means 1 and 2. 3 will not come because 3 is there in T. Like that, T difference S is the set of those elements in T that are not in S. Or in other words, the set of those elements that are in T alone. And finally, the Cartesian product of S and T will consist of these ordered pairs 1, 3, 1, 4, 2, 3, 2, 4, 3, 3 and 3, 4. Then exercise 2. Let R be the set having these elements A, B and C, comma, S be the set consisting of the elements A, C and D, and T be the set consisting of C, E and F. Find R intersection S. That's one thing. Then R intersection S difference T. Then S union T. Then S intersection R union T. And finally the Cartesian product R cross S. So first we need to calculate the intersection. So we look for common elements. There are two, A and C. So this set consists of A and C. Then R intersection S difference T. We can calculate this in two stages. First we keep R and calculate S difference T. That means we have to consider those elements in S that are not in T. Now what are the elements common to both S and T? C. A and D are not there. So that means S difference T is the set consisting of A and D. And when you take the intersection of this set with R, then there is only one common element, that is A. B and C are not present here. Then S union T, all the elements in S, that is A, C and D, along with all the elements in T. C is already there in S, so we are not going to write it once more. The extra elements are E and F. Then S intersection R union T. So like this one, we first calculate R union T. R union T has these elements A, B, C and the ones in T. C is already there, so E and F, and this becomes equal to, so what are the elements common to S and this set? S has the elements A, C and D. A is there, C is there, but D is not there. So that means A and C. And finally R cross S. It's a Cartesian product, so its elements will be ordered pairs. The first coordinate will be A and then B and then C. So for A, and since the second set is S, so we have to take all these elements one by one as second coordinates. A comma A, A comma C, A comma D, then B comma A, B comma C, B comma D, and then C comma A, C comma C and C comma D. Then 3, let R, S and T be sets. With R a subset of S, show that R union T is a subset of S union T. Okay. So to prove that this is a subset of this, we have to prove that every element here is also present here. So let X be any element in R union T. Then X belongs to R or X belongs to T. And you already know that this OR is inclusive OR. That means this statement means either X belongs to R or X belongs to T or X belongs to both R and T. That possibility is also accounted for. So that's why it's called inclusive OR. It doesn't mean that exactly one of these two things is true. That's not the meaning of this statement. Okay, so this implies x belongs to S or x belongs to T since R is a subset of S. So when x belongs to R, x will also belong to S because R is a subset of S. And if x belongs to T, then of course x belongs to T. Hence, x belongs to S union T because x is now either in S or in T or in both. This shows that R union T is a subset of S union T. Now when you go through this type of proofs, it's a simple proof of a fact, it's nevertheless a proof of something. A question may arise in your mind, okay, what have we proved here? We have proved here that when x belongs to R union T, then x also belongs to S union T. What if x does not belong to R union T? In other words, if the situation is such that you cannot take any element x from R union T, or in other words, what happens if R union T is empty? If R union T is empty, then this statement, only this part, is false. If R union T is empty. But in that case also, this implication is true, it is vacuously true. So when considering this, when beginning a proof like this, there is no need to assume that R union T is non-empty, so that you can take some element there and then carry out the proof with that element, because if R union T is empty, then the implication is vacuously true. So you don't have to think about this extra. So that means there is nothing logically wrong with this proof, and this type of proof can be started and are started like this. And the case where you actually cannot choose anything from R union T, that is when R union T is empty, is also giving rise to a true statement, although it's vacuously true, but it is still true. So in this case, you can write, if you want to write about this special case, in this case the implication is, the entire statement is vacuously true. Then the fourth one, let S be the set of the first n positive integers for some positive integer n. Okay, show that S has 2 to the power n subsets. This exercise I have already solved, but let us still solve it once more. One can prove this fact either by induction on n or by using the binomial theorem. So we are going to use binomial theorem. The induction proof is already there. You can search in the videos on Terence Tau, I think, or you can also search in the topics in algebra videos. Okay, there we have proved this fact. Okay, so now what is it that we have to prove? We have to prove that the set S has exactly 2 to the power n number of subsets. So any subset of S will have at most n elements because it is a subset of S. So that means the subsets of S can be divided into classes like this. The subsets of S which have no elements at all. There is only one such subset, which is the empty set. Then the subsets of S, each of which has exactly one element, that is singleton subsets, then 2 element subsets, 3 element subsets, and so on. And we can calculate the number of each such class of subsets. So we write like this: S has, and in calculating those numbers we are going to of course use the ideas from combinations. S has n choose 0 subsets with 0 element. And we continue this sentence: n choose one number of subsets with one element. N choose 2 number of, I wrote number, subsets each having 2 elements, and so on. Finally, the largest subset will have exactly n elements. N choose n subsets with n elements, and that's the upper bound. S can have no subset with more than n elements because S itself has n number of elements. And you can clearly see that any subset of S will be one of these types. So the total number of subsets of S is n choose 0 plus n choose 1 plus n choose 2, etc., plus n choose n. And this, according to our usual binomial expansion, is 1 plus 1 whole to the power n, that is 2 to the power n. So that's how S has exactly 2 to the power n number of subsets. Okay, then a set theoretic identity. Let R, S and T be any sets then show that R union S intersection T is equal to R union S intersection R union T, which is also expressed by saying that union distributes itself over intersection, just like multiplication distributes itself over addition. It looks something like this: A dot B plus C is equal to A dot B plus A dot C. I mean, the structure of the equation is like that. This is you can compare this union operation with multiplication and intersection operation with addition, at least in terms of the structure of these two equations. You can see that they are similar. So this is one of the distributive laws. The other distributive law you can obtain by interchanging union and intersection. So we now have to prove this, where R, S and T are any three sets, and in any such set theoretic identity or any equation where both the sides are sets, that to prove such an identity, the standard technique is to show that each one is a subset of the other. We prove that R union S intersection T is a subset of R union S intersection R union T, and also the reverse inclusion. R union S intersection R union T is a subset of R union S intersection T. So let us prove this one first. We have say we are choosing any element here, R union S intersection T. By the definition of union, this means that either X belongs to R or X belongs to S intersection T, or both. Okay, that is included here. Now this implies X belongs to R, or okay, I need ink. Or X belongs to, now intersection means X has to belong to both S and T. Now this implies X can be in R or X can be here. It is equivalent to write X belongs to R or X belongs to S and X belongs to R or x belongs to T. Why? You see, any two of these statements is true. Any one of these two statements is true. Either this is true or this is true, or both are true. If x belongs to R, then of course this statement is also true and this statement is also true, because x belongs to R. In each one of them, each one of these two statements is an OR statement, a disjunction. So a disjunction is true if at least one of its parts is true. So if x belongs to R, then the first statement is also true and the second statement is also true. So that means this is true and this is true. Okay, so we can write this. Now what happens if the other statement is true? If this is the case, that is if x belongs to S and x belongs to T, then also both these statements are true, because in the first statement we need either x to be in R or x to be in S or both. Because x belongs to S, so this part is true. X may or may not belong to R, we don't bother about that. In OR, a truth of at least one part is enough for it to be true. So since x belongs to S, this statement is true. Like that, since x belongs to T, this second statement is also true. So in all the cases, this is true and this is true. So that's why this implication makes sense. Okay, now we can use the definitions of union and intersection. First, inside, in the first one, x belongs to R or x belongs to S implies x belongs to R union S. And just like that, the second one implies x belongs to R union T. Now because we have AND, this would imply x belongs to R union S intersection R union T. So any element in this set also belongs to this set. Thus, we have proved the first inclusion. R union S intersection T is included in the second set. R union S intersection R union T. Next, we have, now we need to prove the reverse inclusion. So we will assume an element here and we will prove that the element also belongs to this one. So let us use another symbol, say y belongs to R union S intersection R union T. So you will see that whatever you write here, they will just be these statements but in the reverse order. So this first of all means y belongs to R union S and y belongs to R union T. Then this means y belongs to R or y belongs to S or both. And the second one means y belongs to R or y belongs to T. Okay. Now this implies you can write this as y belongs to R or y belongs to S and y belongs to T. But remember, whatever you write, you have to justify, at least to yourself. How is this implication true? Let us see. This and this means both this is true and this is true. Okay. And that should imply this. Actually, that's not exactly entirely correct what I have said right now. This and this means both this is true and this is true. No. If they are true, if this and statement is true, then this is true. That's what this implication means. Okay. That's what I am trying to say. So, suppose that this is true. That means this is true and this is true. Now, the first can be true in two ways. Either y can belong to R or y can belong to S. Suppose y belongs to R first. Then here in this statement, the first part is true. So because this statement is an OR statement, truth of the first part implies the entire OR statement is true. Now, suppose the other possibility is there, y belongs to S. Then you don't know anything about this part. But here y belongs to S is there, that is true. But at the same time, you have this also. No? So here, suppose y belongs to T. Now you can ask me, why should we assume that y belongs to T? It can also happen that y belongs to R. No? But if y belongs to R, then we go back to that first case. So that means now we are next assuming the case where y does not belong to R. Now because both these statements are true, y not belonging to R means y has to belong to S and y has to belong to T. So that means this is also true and this is also true. So that's why this second part of the OR statement is true. That means the entire OR statement is true. So you see that if this is true, this AND statement, then in all the possibilities, the OR statement is also true. So this implication is correct. Now, we can of course again use the definitions of union and intersection. S intersection T and because you have OR, R union S intersection T. If the way we are arguing in deciding that these implications, intermediate implications are true, seems very complicated to you, that is because if you think of the possibilities, it is complicated and it's very easy to make mistake. Make mistake in this sense that you may fail to account for some possibility, you may miss some possibility. So that's why there are some rules in mathematical logic which will help us deal with OR and AND statements. If you want to know about those rules, I will recommend the beginning videos in Terence Tau's analysis one that we have. Okay, you go through those videos, there you will see that you have these general logical rules which are true. That say you have three statements, then P or Q and R, say P, Q and R are three statements, sentences which are either true or false. Then this statement is P or Q and R. This statement looks like that, no? Which one? This one. P is y belongs to R, Q is y belongs to S, R is y belongs to T. So this compound statement is of this structure. This is logically equivalent to this compound statement. These things are already available and they can be proved. What this means is that if this is true, then this is true. If this is false, then this is false. That is, these two statements, compound statements, are either both true or both false. They are simultaneously true or simultaneously false. So if you use one half of this, say this one, PRQ and PRR implies PRQ and R, then you can directly write from this compound statement, you can directly write this one is also, this one follows from this by using this law from mathematical logic. It's also a distributive law. But if you don't want to go into those things, you can also simply argue like how we have done here. Okay, so that means we have proved that any element in this set is also present here. Hence, the worst thing that one can do here is to memorize these steps without understanding anything, so that when the person sees this, he or she will automatically write this, but won't know why that is true. That is the worst thing. So now we have proved that both the inclusions are true, so that's why the sets are equal. Thus, R union S intersection T is equal to R union S intersection R union T, and that's how we have proved the identity. You don't even have to memorize these steps. If you practice these things enough, at least mechanically, if you start writing these things enough number of times, you will automatically start to remember what to write after a certain statement without ever understanding why you are writing what you are writing. Okay, so that is the danger, and that is the point where it seems you know about the things, but actually you don't understand anything. Okay, now this next one, for each positive integer n, let Tn be the set of all numbers which look like this, a divided by n, where a is an integer. Okay, it has two parts. Part 1 asks us what is the union of the sets Tn, as n varies over all the positive integers, and the second part asks us about the intersection. Okay, part 1, note that Tn is a subset of the set of rational numbers for all positive integers n, that is for all n belonging to n. N is the set of natural numbers, and in this book natural numbers are by definition positive integers. Okay, 0 is not included in n. Hence, so if Tn is a subset of Q for every n, so the union of all the Tn's will also automatically be a subset of Q. Hence, this is a subset of Q. Okay. Now let R be any rational number, then by the definition of rational numbers, there exist integers m and n, where n is positive such that R is equal to m divided by n. R itself can be negative also, or R can be 0 also. The positivity or negativity or zero-ness of R is taken care of by m, the numerator. We can always choose n to be positive. So if you are thinking what happens when R is negative, say R is equal to minus 2 by 3, then you can write this as minus 2 divided by 3. So you always can make the denominator positive. This implies that R belongs to Tn, because you see R has the form m divided by n, where m is any integer and n is a positive integer. So R belongs to this particular Tn, and hence R also automatically belongs to the union of all the Tn's. So that means any rational number also is there in the union. Thus, the set of rational numbers is also a subset of the union of the Tn's. We thus have the union of the Tn's equal to the set of all rational numbers. Okay, so the union of all the Tn's is equal to the set of rational numbers. Now we figure out the intersection. Note that what is T1? T1 consists of all numbers of the form a divided by 1, where a is any integer. That means T1 is nothing but the set of integers. So the intersection of all the tn's is definitely the intersection of all the tn's is contained in every tn. In particular, it's contained in t1. It's a subset of t1. So that means it's a subset of z or c, the set of integers. Now let a be any integer. Okay. Then for every positive integer n, we can write a equal to an divided by n, where an is an integer. Because a is an integer, n is a positive integer, their product will be an integer. So you can see that any integer a can be written in this form, and this form tells us that a belongs to Tn. This implies a belongs to Tn, and that too, this is true for all positive integers n. For any positive integer n. Thus, the set of integers is also contained in Tn for all natural numbers small n, or all positive integers small n. We thus have the set of integer as a subset of the intersection of all the tn's. So you combine these two inclusions and write the intersection as the set of integers. Okay, so it turns out that the intersection is the set of integers. Let us now go to some exercises. That's all we have about sets. Next, relations. Let S be the set consisting of the numbers 1, 2 and 3, and T be the set consisting of 3, 4, 5, 6, 7 and 8. Define a relation rho from S to T via this rule where A is related to B, that is A rho B, if and only if this inequality is true, the absolute value of a square minus b is less than or equal to 1. So that's how we have defined this relation from S to T. Find all pairs of related elements. Find all pairs A comma B belonging to S cross T such that A is related to B. Because this is just a matter of calculating those pairs. Okay, so if we take our A to be 1 here, then what can you take as B? Keep in mind that the B has to come from T. Now if we take A equal to 1, then 1 square is 1. Now the difference between 1 and 3, the numerical difference is 2. And the difference between 1 and the other numbers are even more. 1 minus 4 is minus 3, its absolute value is 3. So none of them is less than or equal to 1. So that means 1 is not related to any element from T. What about 2? If we put 2 here, then we will get 4. Now if we have 4 here, then we can take B equal to 3, because 4 minus 3 is 1 and 1 is less than or equal to 1. So that means if B is, okay, we have to write like, or we can write like pairs also, but I think it's better to use this notation because that will at once show which ones are related to which ones. So if our A is 2, then 2 is related to 3, because 2 square minus 3 is less than or equal to 1. It's in fact equal to 1. Okay, now this is 4, that is fixed, and we can of course take B equal to 4. So 2 is related to 4 because 4 minus 4 is 0, and we can take B equal to 5 also, because 4 minus 5 is minus 1, its absolute value is 1. So that means 2 is also related to 5. But the difference between, if we take the higher values of B that are available, say 6, then 4 minus 6 is minus 2, 4 minus 7 is minus 3, 4 minus 8 is minus 4. All of them have absolute values greater than 1. So that means the other B values are not related to 2. Okay, then the only other possibility is you can take A equal to 3. When A is 3, this is 9. Okay, now when this is 9, you cannot take B equal to 3 because 9 minus 3 is 6. Can you take B equal to 4? No, 9 minus 4 is 5. Can you take B equal to 5? 9 minus 5 is 4. Then 9 minus 6 is 3. 9 minus 7 is 2. 9 minus 8 is 1. Okay, so that means 3 is only related to 8. 1 is not related to any element from T. 2 is related to 3, 4 and 5. And 3 is only related to 8. So these are all the possible pairs. If you want to write them as pairs, you can write 2, 3, 2, 4, 2, 5 and 3, 8. Okay, then, so that's just it. If you want, you can make the solution a bit longer by actually showing the calculations. Okay, then 1.8, that is 8. Define a relation row on the set of integers where A row B if and only if. So here you can see that the sets S and T that were involved in this relation row were different, but we can of course take both the sets to be the same. So that is the case here. Here the first set is the set of integers, as is the second set. So this if and only if, okay, this time the definition of the relation is A is related to B if and only if AB is an even integer. And the question is this: is the relation reflexive? Is it symmetric? Is it transitive? For reflexivity, every integer has to be related to itself, which however is not true, since 1 square is not even, 1 is not related to itself. Thus, row is not reflexive. Okay, what about symmetry? Row will be symmetric. For that, we consider two integers, this, such that A is related to B, that is AB is an even integer, then BA is also an even integer, because AB and BA are the same thing, and hence B is also related to A by this relation. So row is symmetric. Now, is it transitive? It is not transitive actually. Note that one is related to 2 because their product is 2, which is an even integer, and 2 is related to 3 because the product of 2 and 3 is also an even integer, it is 6, but 1 is not related to 3 because their product is an odd integer, it's not even. Hence, row is not transitive. So that means row is only symmetric, it's neither reflexive nor transitive. Next, the next one is also similar. A number of them are there which are similar. define a relation rho on the set of real numbers this time. On the set of real numbers, we have this rule: if and only if their difference is a rational number. Okay, is rho, again same, reflexive, symmetric, transitive. I think it will be. Let us see. Note that for any real number a, a minus a is 0, which is a rational number. Thus, a is related to a, and hence rho is reflexive. And rho will also be symmetric, and it will also be transitive. The fact that these things are true actually is happening because the set of rational numbers is a group under addition. Next, let a and b, oh, now we cannot, okay, is it happening because of that? Yes, because even if the parts in the difference a minus b may not be rational, but once the difference is rational, then we are inside the system of rational numbers. Let a and b be real numbers such that a is related to b, that is a minus b is a rational number. Then b minus a is also a rational number. You just have to take the additive inverse or the negative, ordinary negative of this. Then this is also a rational number, and hence b is also related to a. So rho is symmetric. And then let a, b and c be three real numbers such that a is related to b and b is related to c. Then a minus b and b minus c are both rational numbers. This implies a minus c is also a rational number because a minus c is the sum of these two rational numbers. And hence a is related to C. So rho is transitive. So this particular relation turns out to be reflexive, symmetric and transitive, all the three things. Next, 10. Define a relation rho on, again, the set of real numbers via this formula. A rho B, A is related to B if and only if this time A minus B is a natural number, that is A minus B is a positive integer. Again, is rho reflexive, symmetric, transitive. Okay, this time I think all the three will not be, the relation will not be all the three. First of all, it's not reflexive, and in fact it's not reflexive in the worst way possible. No real number is related to itself. Forget about all the real numbers being related to themselves. For any A belonging to R, we have A minus A, which is 0, not belonging to N, that is A not being related to itself. So rho is not reflexive. Actually, we need not have written it in this general manner. One example was enough. Say 1 minus 1 is equal to 0, so 1 is not related to itself. But I just wanted to show the extent of non-reflexivity, if you want to call it. Okay, then next, symmetry. It will not be symmetric also. You see, note that A minus B, so 2 is related to 1 because 2 minus 1 is 1, which is a natural number, but 1 is not related to 2. Because 1 minus 2 is minus 1, it's not a natural number, it's a negative integer. One is not related to 2 because this does not belong to N. So rho is not symmetric. However, it will be transitive. Let A, B and C be three real numbers such that A is related to B and B is related to C. Then A minus B and B minus C are both natural numbers. So a minus c, which is their sum, is also a natural number. Sum of two positive integers is again a positive integer, which implies a is related to c. Thus, rho is transitive. Okay. Next, exercise 11. It has two parts. Part 1 says how many relations are there on the set 1, 2, 3, and part 2 asks how many of these relations are symmetric. As a solution, we will simply write the numbers and we will complete the solution there itself. However, the justification of why those numbers are true, or rather how one obtains those numbers, that we are giving after the solution. Okay. Number 1, the number of relations. So here in writing these solutions, we take the view that we are supposed to know how to calculate these numbers. We know the formulas. The number of relations on is 2 to the power 3 times 3, that is 2 to the power 9, and among the above relations, the number of symmetric relations is 2 to the power 3 times n times n plus 1 divided by 2. That means, how much is this? 2 to the power, so this will be 4 divided by 2, so 2 to the power 6. But what are these powers of 2? Let us see. The first one is not that difficult. We have been asked to calculate the number of relations on the set 1, 2, 3. So you just go to the definition of a relation. A relation on this set, by definition, is a subset of this Cartesian product. So you just have to calculate the number of subsets of this set. Now, how many elements does this set have? 3 times 3, that is 9 elements. So in this video itself we have proved that a set having n elements has exactly 2 to the power n subsets. So the number of subsets of this set is 2 to the power 9, and since each such subset is defined to be a relation on this set 1, 2, 3, so the number of relations is 2 to the power 9. The second one, however, is not that straightforward, but it can also be understood. Okay, so what do we need for symmetry? For symmetry, we need this. If say 1 is related to 2 by some relation, for it to be symmetric, 2 should also be related to 1. Okay. Now, if you think of a rectangular arrangement of these elements, say like this, then here you have all the possible ordered pairs. So this actually is just a rectangular representation of this Cartesian product. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Now, taking some of these ordered pairs together, we will get a relation, because a relation by definition is a subset of this. So that means if you collect some, maybe not all, but some ordered pairs from this, then you will get a relation. Okay, so now in such a relation we want symmetry. So that means if, for example, we have 1, 2 in that relation, then we also need 2, 1 to be there. Now 1, 2 being there or not being there, we can express this by considering 0 and 1. Say you can think of a relation on this set 1, 2, 3 in this way. Say I put some zeros and ones in these boxes. What does this mean? It means that whenever you see 0 somewhere, that corresponding element in that same box is not there in that relation. And if you see 1, that means that corresponding element is there in the relation. So this arrangement of zeros and ones tells us that this represents this particular relation, where the element 1, 1 is not there. So we don't have to think of the zeros. 1, 2 is there because we have 1. Then in the second row, 2, 1 is there because here we have 1. 2, 2 is there, and then one more is there, 3, 3. You can see that this relation is symmetric, because whenever you have a comma b, b comma a is also there. A comma b and b comma a for these two elements are the elements themselves. But if this is your a comma b, then this is your b comma a. So we never encounter a situation such that a comma b is there but b comma a is not there. That's how we have chosen this relation. So the point here is that this relation is symmetric, and according to this somewhat strange way of representation, you can see that this table means this relation. But what is the need for this? The need for this is that these ones and zeros help us keep track of which elements are there in this relation. Okay, so now for the relation to be symmetric, what can we say about the arrangement of ones and zeros? We can see that if you look at this diagonal, for symmetry, the elements which are mirror images of each other on this diagonal, they should be the same. You see, here you have 0, here also you should have 0. If you had 1 here and 0 here, then according to this arrangement, in our relation 1 comma 3 would be there, but 3 comma 1 would not be there. That will make the relation not symmetric. We don't want that. So we want the elements which are mirror images of each other on this diagonal to be the same. That is, if we have 1 here, then we have 1 here. If we have 0 here, then we have 0 here. We have 0 here, we have 0 here. These things. And what this tells us is that for symmetry, once you choose what the elements above this diagonal are, automatically their mirror images are also chosen. You cannot change them. Okay. And for symmetry, this is enough. It does not matter what you put here, whether you take 1 here or 0 here in each of the boxes above the diagonal. The below diagonal boxes are automatically determined. They also have to be correspondingly equal, and hence that will make the corresponding relation symmetric. So that means we can freely choose only the boxes above the diagonal. And what about the boxes on the diagonal? They may or may not be there. You can also freely choose the elements here. Whether you have or you don't have 3 comma 3 here does not affect symmetry of this relation. You can choose to not have 3 comma 3. For example, we don't have 1 comma 1 here. If you put 1 comma 1 here, then also that relation is symmetric. If you remove it, then also the relation is symmetric. So these entries don't affect symmetry of the relation. So they can be freely chosen, and this can also be freely chosen. Now each box can be chosen to be either 1 or 0. Correspondingly, the element that is there in the box, the ordered pair, is either in the relation or not in the relation. So that means for each box we have 2 choices, either 0 or 1. Now how many boxes are there in the above the diagonal? In this particular case, the number of boxes is 1, 2, 3. And how many are there on the diagonal? 1, 2, 3. So that means, including the diagonal, the boxes that we have in this portion are 3 plus 3 equal to 6 in number. So if you independently choose each such box to be either 0 or 1, so the total number of choices will be 2 to the power 6. So that's how you get this number. But why have I written 3 times 3 plus 1 divided by 2 here? That comes from the general situation. If instead of having 1, 2, 3, you had say this, then you would have to consider an n by n box. There, if you calculate the number of boxes on the main diagonal and also above it, it turns out to be n times n plus 1 divided by 2, and you can see why that is true. You can count the number of boxes on the diagonal and above the diagonal row wise. In the first row, in the bottom row, you have only one box. In the row above that, you have 2 boxes. Then the number increases 1 by 1. In the topmost row, you have n boxes. So the total number of boxes is 1 plus 2 plus 3, etc. up to n, which is equal to this. So the number of symmetric relations is 2 to the power this. That's what we have used here. Okay, so the total number of relations is 2 to the power 9 and the number of symmetric relations is 2 to the power 6. And finally, exercise 112, for each of the 8, the way this exercise has been put, it looks really nice. You will see why. The exercise itself is not that interesting, but the way it has been written is very interesting. For each of the 8 subsets of these adjectives, reflexive, symmetric, transitive. Find a relation on the set 1, 2, 3 that has the properties in that subset but not the properties that are not in the subset. So that means Lee is asking us to give examples of relations on this set that is neither reflexive nor symmetric nor transitive, then only reflexive, then only symmetric, only transitive, then reflexive and symmetric but not transitive, and all such possibilities. So all of those things he has expressed at once like this. You can probably understand what he is trying to say. He has taken these adjectives, reflexive, symmetric and transitive themselves, and he has made a set of adjectives. And this set itself has many subsets. For example, one subset of this set is the empty set. That corresponds to an example of a relation on this that is neither reflexive nor symmetric nor transitive. If you think of the subset of this consisting of only the adjective reflexive, then that means we have to find an example of a relation on this set that is only reflexive. So let us now find those examples. I am not going to write the things systematically. I will just simply indicate the subset and a corresponding example. Okay, so empty set means the example that we will have here is neither reflexive nor symmetric nor transitive. Okay, for a relation to not have any of the three properties, reflexivity can be broken by not including some pair of same elements. Symmetry can be broken by taking one pair and not taking the other. That is, for example, by taking A comma B and not taking B comma A. And transitivity, of course, can also similarly be broken. So what happens if we take 1 comma 2 and 2 comma 3? So this of course is a relation on this set, because why? Because this is a subset of this set, Cartesian product, again this set. This relation is not reflexive because, for example, 1 comma 1 is not there. It is not symmetric because 1 comma 2 is there but 2 comma 1 is not there. And it is not transitive because these two pairs are there but 1 comma 3 is not there. Okay, so it is neither reflexive nor symmetric nor transitive. Then we say want only reflexivity. This already has been not symmetric and not transitive. So we try to make this reflexive by including all such A comma A's. One comma 2, 2 comma 3. It is reflexive because now you can see all these three pairs are there. But because of the presence of 1 comma 2 and absence of 2 comma 1, it's still not symmetric, and because we don't have 1 comma 3, it's still not transitive, so it's only reflexive. Then for a relation to be only symmetric, we need to not have transitivity. Okay, so let's break transitivity by having these two and not having 1 comma 3. But because we want symmetry, we would have to include 2 comma 1 and 3 comma 2. So symmetry is okay. We don't have reflexivity because these elements, none of them is here, and transitivity of course is not true. Then we want say only transitivity. For that to happen, we can consider this relation. So 1 is related to 2 and 2 is related to 3. 1 is also related to 3, but you have to see all the possibilities. If you start with 1 related to 3, but then you cannot form such a pair because here we don't have 3 comma something. So there is no problem if we start with 1 comma 3 because we cannot form such a situation where 1 comma 3 is there and 3 comma something is there. Then we need 1 comma something to also be there. Okay, now if you start with 2 comma 3, then again 3 comma something is not there. So that means this relation is transitive. It is not reflexive because of the absence of these things, and it is not symmetric because 2 comma 1 is not there. Okay, then reflexive and symmetric but not transitive. Okay, what can we do for this? First of all, we have to have this for reflexivity, these 3. So let's write them first. And we don't want transitivity. So let us take 1 comma 2 and 2 comma 3, but we won't write 1 comma 3. That will break transitivity. But we want symmetry, so we need to include 2 comma 1 and 3 comma 2. Okay, so this is reflexive and symmetric but not transitive. Then symmetric and transitive but not reflexive. For that we can remove one of these 3. But we want symmetry and we want transitivity. This is transitive. We can make this symmetric. By including the other pairs 2 comma 1, 3 comma 2. Oh, but then what about transitivity of the other? I think there is a much easier example. And that easier example is this. There is no problem with symmetry here because the only pairs are a comma a. So the other corresponding pair, the other pair for a comma b is b comma a. That is also the pair itself. So it's there. So it is symmetric. And transitivity also similarly is trivially true in this case. However, this is not reflexive because 1 comma 1 is not there. And then reflexive and transitive. But not symmetric. And we don't want symmetry, right? So say we have 1 comma 2. Okay. Is that enough? Let us see. There is no problem with reflexivity. Symmetry is also not there. Now we need to check transitivity. If we have 1 comma 1 and 1 comma 2, then we need to have 1 comma 2, which is here itself. If we take 2 comma 2, then 2 comma something, that is this one itself, so no problem. If we take 3 comma 3, then and 3 comma something, so that also is this one only, so there is no problem. If we take 1 comma 2, then 2 comma something, that is this one, so 1 comma 2 and 2 comma 2, that means 1 comma 2, which is here. So yes, this is transitive. And finally all the three, everything. Reflexive, symmetric and transitive. Since for that we need everything to be there, so why not take all possible things, that is the entire Cartesian product. Okay, this is going to be reflexive, symmetric and transitive in a trivial way, but there is another example for this, which is also very easy, but it may be slightly confusing. The empty set is also a subset of 1 comma 2 comma okay, not a subset of this, I mean it is a subset of this, but it's a subset of this. Okay, so that means this is a relation on this. By this relation, no element is related to any element. The fact that this relation is, oh no, what I am saying is not correct, no. This relation will be symmetric and transitive vacuously, however it will not be reflexive. Okay, no, this is not an example, so you can take this one, and that completes the solution. So with this I am ending this video also. So the next calculus video is, I have already said yesterday when it is. And what about the next upload on these exercises? I will do that. Today is what? Today is Saturday. So next Saturday again I will upload from Lee's Algebra. So that will be all for tonight. If you have anything to say about these things, you can write in the comment section below, or you can mail me here at this address. So see you in the next video. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.